can post this for anybody who couldn't show up. And so we did a chapter on aldehydes and ketones yesterday. And again, those are the top 3 goals for that, you know, the nomenclature and properties, the kind of interesting ability for it to do that eno-keto tautomerism, which leads to different reactivity. And then the reactions we had, mostly reductions and reactions with Grignard reagents. So those are, you know, and then a couple oxidations. And so we have just a few, we're adding a few things to that. Notice that we were making carboxylic acids in the last chapter. And so we're going to go ahead and look at that next level of functional group, which is the carboxylic acid today. Okay, so here we go. I am going to try to share my screen. Screen share, my iPad. There we go. Okay, so again, this is the top 3 goals for learning in chapter 13, carboxylic acids. Okay, now in the videos, there's a lot more detail about reactions and such like that. So don't skip the video by just thinking you got everything here. Here, this gives you the base things to start with. And then once you learn this core knowledge, you can build on it using that, the video and or book. I mean, some people are pretty good book learners, and so you can use that as well. Okay, I'm gonna put the pictures up over here on the big screen, and now I'm going to look at you. Okay, so for our chapter 13 goals, we're going to have nomenclature and properties. We have some of the same properties we had before, and we introduced the topic of carboxylic acid properties being, it is the highest level, okay? So, but there's some subtleties as far as their derivatives go that we'll have to worry about. Our goal 2 is the fact that the carboxylic acids are acids, and therefore they have to be, we have to look at their acid-base properties associated with them, the acid itself, and then its conjugate base. And we've already talked about the fact that carboxylic acids have resonance structures that help stabilize the charge. And we're going to look into that a little bit more. And then we're going to go into some of the reactions. And most of the reactions we're going to go at on goal 3 are associated with making derivatives of them or reacting them to make them into other functional groups. So, but we're going to start with goal 1 right now. Okay. So as I said before, this is the second of 4 chapters where we're going to look at the functionality, the carbonyl functionality, that's C double bond O. And in the previous case, we had the C double bond O bonded to 2 carbons or a carbon and a hydrogen, okay? Now, remember that carbon-carbon bond and that carbon-hydrogen bond are fairly non-polar, okay? So the idea is that those are not as reactive as other things. Once we add an electronegative atom like oxygen to our carbonyl, we gain reactivity, okay? So that's why we put them all together, because what we're doing is we're changing that reactivity at that carbonyl here. Okay, so we can have 2 or 3 different ways of looking at it. And so when I go to my pen here, this is what it looks like if we try to draw our Lewis dot structure. And remember, when we made it into our resonance structure, these electrons kick in and these electrons kick up, giving an anion here. Okay, so that's our resonance structure for the acetate ion. And that's a very common way to look at that. And so that's why the Lewis dot structure is drawn here first. But sometimes we shorten it to COOH. Okay, and occasionally that's C2H, okay? I like the COOH right here because it tells you there's an OH plus the carbonyl. So it kind of reminds you that there's a carbonyl as part of the functionality and an OH as part of the functionality. But it's also very commonly done with this CO2H. But just remember that any of these structures actually gives us that carboxylic acid function, which has that acidic proton. And that's probably one of the first things that may or may not react in our system. We just need to pay attention. Okay, so most of the time, if it's aliphatic, we can just use any old R group. It can be a ring, it can be a straight chain, doesn't matter. But occasionally we introduce the topic of the aromatic carboxylic acid in the benzenes chapter. And we say that is the AR. AR is telling you you have at least a benzene ring there, maybe something else, okay? So when we look at carboxylic acids, it is the highest thing. If you have a carboxylic acid on that compound, you're going to name it for the carboxylic acid. And the way we do that is we take our longest chain or our ring, and we drop the E at the end and put oic acid, okay? So in the first case of this first one here, we have 1, 2, 3, 4 carbons, including the carbonyl carbon. We have to include the carbonyl carbon in our parent chain. And so we have 4 atoms there, so that makes it butane. But we drop the E and add oic acid, so it's butanoic acid, okay? Now, just like with the aldehydes and ketones, if it was named for the aldehyde or ketone, we start with the carbonyl carbon as carbon number 1 when we're numbering, 2, 3. So in this case, we have 3-methyl butanoic acid, okay? This particular acid is fairly small and common, and so we actually have a common name for it as well. And so this is called isovaleric acid, okay? Valeric acid would have the methyl group over here. And so, and the valeric acid actually turns out to be a kind of a smelly compound. It's used in a, it's found in a plant called, not Vallisneria, but it's a very stinky material that's also found in the same material you get a valerian root from, and valerian root is also used as a sleep aid for some people. It's a natural sleep aid. Okay, so let's look at how we would name this if we had another chain on here. We have a total of 1, 2, 3 carbons in our chain, which gives us our propane. That's our base. Remember, when we have a benzene ring on the system, we name it for the longest aliphatic chain, if at all possible, and then the benzene ring becomes a substituent. We call that the phenyl substituent, okay? So that means our longest parent chain here is 3 carbons long, therefore we have propane. Drop the E, add oic acid, so we have propionic acid right here. And we have 1, 2, we have a double bond here, okay? So we have to figure out where to put that E for the double bond. Notice instead of being propaneonic acid, this is not an A, this is an E. That E is because of the double bond, okay? So because that's the first carbon we can have it there, we actually don't have to say it's the 2 carbon that the double bonds on. However, if we had that double bond somewhere off on the ring, remember we have to have that first carbon in the double bond in the name, okay? And we have our substituent on our last carbon. So this is, again, because we're naming from the carbonyl, this is 1, this is 2, this is 3, which means our phenyl group is on the number 3. So that's where we get our 3-phenyl from. And the trans comes from the fact that the substituents are on opposite sides of each other, and therefore we have our trans configuration. Again, we only have 2 substituents, so we don't have to worry about E and Z, but we do have to worry about cis and trans. And so we can say it's the trans 3-phenyl propionic acid, okay? See, and there's that note that says we don't have to say it's on the 2 position because there's no other place for it, but in most times you will have to do it. Notice that we can have an ANE or an ENE. You can even have a YN if you have a triple bond in the compound somewhere. So the single bonds only is the A, the double bond is the E, and the YN would be if you actually had a triple bond somewhere else. But again, the carboxylic acid is naming the compound. Excuse me. All right. So let's go ahead and look at this here. Now, whenever we have any other group, if we did not have this carboxylic acid here, right here, we would name it for the alcohol, right? Because that is one of our functional groups that changes the name. But because we have it, it takes precedent. And when we have an amine, and amine is one of the lowest priority ones, that's below even alcohol. And so you would name it for anything higher, like the alcohol or the ketone or the aldehyde. But again, the carboxylic acid takes, and again, this is an ester, I'm sorry, a ketone right here. And the ketone, when we have it on a group with a carboxylic acid, we have to tell you that it's a C double bond O oxygen. Notice it's hydroxy here because it's a COH bond. When it's a C double bond O, a carbonyl, we have to use the prefix oxo. And again, we start numbering at the carbonyl carbon of the carboxylic acid. So it's 1, 2, 3, 4, 5. So our carbonyl is on that number 5 carbon, which gives us the 5-oxo. And there's a total of 6 carbons, which would be hexane. So it's hexanoic acid. Okay, I'm going to take that writing away so you can see that. Okay, so because the carboxylic acid takes precedent and the carbonyl carbon is number 1 when you're numbering it, it actually is fairly easy to number these things because you know you have to start with the carboxylic acid. Okay, well, what if you have more than one carboxylic acid? Well, if you have more than one carboxylic acid on the system, we get to use di, tri, or tetra in the system. So in the case of just 2, we would say instead of hexanoic acid, it would be hexadioic acid, okay? Hexane dioic acid right here. So you have your parent chain. Notice that that's including the carbons of the carbonyl in the parent here. There's a total of 6 carbons, including both of the carboxylic acids, to get our hexane. And then we have the hexane dioic acid. Okay, notice here we only have 2 carbons, so that'd be ethane dioic acid. 3 carbons, 4 carbons, 5 carbons gets us to pentane dioic acid. Now, there's also common names for these. And when we use the common names here, there's actually a good way to remember the first 5 of these dicarboxylic acids, and because they're oxalic, malonic, succinic, and glutaric, and adiptic, we go, oh my, such good apples. And that gets you your first 5 dioic acid common names. So, oh my, such good apples. Oxalic, malonic, succinic, glutaric, and adiptic. But the IUPAC name is always correct. And it's, again, total number of carbons, including your carboxylic acids, and then dioic acid to show that you have 2 of them there. Okay, questions on that? Somebody type something in the Zoom chat. I don't believe anybody's listening.
We're listening.
Type. Okay, so just like for aldehydes and other ketones, okay, great, thank you. Somebody typed in. All right, just like with the aldehydes and ketones, whenever we have a ring, we name the ring for what it is. For example, 6-membered ring would be cyclohexane, and then we add the word carboxylic acid. Remember when we had aldehydes, we said carboxaldehyde. When we had a ketone, it's usually actually in the ring, so we just call it a ketone. In the case of our carboxylic acids, we name the ring, and then we add carboxylic acid. Okay, so in this case here, we have a total of 6 carbons in a ring, but we have a double bond in the ring. So that gives us cyclohexene. Okay, so that's our pair. That's our parent right there. And then we add carboxylic acid to it right here, but we have to identify where the alkene is. And remember, when we name a ring for a substituent like that, that becomes number 1 in the slot. Okay, so we know that this carbon, because we're naming it for the carboxylic acid, is always number 1. Just like if it was the alcohol, this would also be our number 1 in the ring. Means that our alkene starts on number 2, and therefore we have 2 cyclohexene, there's an ene there, carboxylic acid, okay? And to apply both the dicarboxylic acid rule and the ring rule, we're gonna do this next one here. In this case, we're gonna say it's 1, 2, 3. It could name the other number, we don't really know because there's not another substituent, but it'd be 1,3-cyclopentane, because of the substitutions here, and it'd be dicarboxylic acid, just like the dioic acid we have on the di, we have dicarboxylic acid here. And because we have stereoisomer possible here, we have to say whether they're cis or trans, okay? Now, notice we could label each of those R and S. However, the cis or trans configuration actually names every substituent exactly where it is. And we could go back and assign S and R to those two different sites, the 1 site and the 3 site. But the trans does fully describe the ring unambiguously. Okay, so when we go to having a carboxylic acid directly attached to a benzene ring, we call that benzoic acid, okay? So that change, because there's no aliphatic group, we now have what we call a benzoic acid here. And because it takes precedent of all the other groups, we actually would name it whatever the substituent is plus benzoic acid. So in the case of this right here, our benzoic acid is our number 1 slot. Our hydroxy is on our 2 position, so that gives us 2-hydroxy benzoic acid, okay? Now the cool thing is that this is also has a common name because it was originally extracted out from willow bark, and it is the core of aspirin, which is acetylsalicylic acid, which is the acetate derivative. We'll learn about that in the next chapter. But so this is actually the base for aspirin, okay? Now, if you have 2 carboxylic acids on there, we're gonna do the same thing we did before. We have benzene dicarboxylic acid, but we have to tell which the positions are. So 1, 2, and then this is 1, 4, okay? And there's also a possibility of having a 1, 3 if you had it there. Now, they have special names, and this particular one is called phthalic acid. Now, one of the interesting things about phthalic acid is it's used as a derivative in plasticizers. So that new car smell is typically phthalic acid derivatives. So the other cool thing is this one right here is called terephthalic acid, meaning it's opposite each other and it's straight. This is commonly used in a lot of things, like if you've ever heard of PET or polyethylene terephthalate, this is used in making that polymer. We'll talk about that in chapter 16. But I want to introduce the topic, but the IUPAC name here is the 1,4-benzene dicarboxylic acid. Okay, so when we go to common names, there becomes a weird thing they do, because in our IUPAC names, we always number the carbonyl of the carboxylic acid as number 1. However, when we go to common names, we start with the carbon that is next to it, and we call that the alpha carbon, okay? So we're gonna use this again in our enolates chapter, which is chapter 15, so pay attention, okay? So in our common names, our alpha is the first carbon with hydrogens away from the carbonyl, and then beta, gamma, delta, okay? So when we use that designation, we know that there's a common name. So if we say, oh, it's gamma something, then you know it's the common name versus the IUPAC name. And in the case of this compound here, we have 1, 2, 3, 4 carbons. So that would be 4-amino butane, which will drop the E and have it oic acid, butanoic acid. But the common name is because this is the alpha, beta, gamma. So it's gamma amido butyric acid. Remember, butyric acid is one of the common names for that 4-carbon chain. Okay. So let's see. So when we have common names that include a group that looks like a CH3 carbonyl, this CH3 carbonyl is typically called, you know how you have isopropyl group, is that the 2 methyl groups with something bound to the middle here? This carbonyl with a methyl group on it is called the acetyl or aceto group, okay? Those are commonly used in common names. So in this case here, we have beta keto butyric acid or acetoacetic acid. So the aceto group here, because this is hooked to it here, this is the acetic acid group, and this is the aceto group, okay? But when in doubt, name it by a IUPAC and you will not go wrong. So by a UPEC name, we have 1, 2, 3, 4 carbons. We have a C double bond O on our third carbon. So it's 3-oxo butane, drop the E, oic acid, butanoic acid. So that's how our nomenclature goes. Now, when we have, oh, we're not, oh, we'd have to draw that out. We're not going to do that. All right, so now let's go to the properties. Okay, the properties of carboxylic acids are defined by their hydrogen bonding. Okay, the carboxylic acids have the highest boiling point for molecular weight of all of our organic compounds. And it has to do with the fact that they form this weird 8-membered ring dimer, where the carbonyl of one of the carboxylic acids is hydrogen bonding to the OH of the other carboxylic acid, and they're binding together in this tight 8-membered ring, okay? This tight 8-membered ring drives the boiling point for all carboxylic acids to be higher than anything else, higher than alcohols, amines, or carbonyls or ketones, okay? So in addition to this hydrogen bonding, it also has a dipole-dipole interaction. We saw dipole-dipole interactions in the aldehydes and ketones bring their boiling points up some, but not as much as hydrogen bonding. So our carboxylic acids have hydrogen bonding plus a dipole-dipole. Therefore, it increases it even more than just a hydrogen bonding would. Okay. So that said, you know, we have the carboxylic acids have the highest boiling for the comparable molecular weight. It has everything to do with the polar compound being a polar compound, having that dipole-dipole interaction, and having that strong intermolecular hydrogen bond. Okay. In addition to that, carboxylic acids tend to be more soluble in water and alcohols than other things of the same molecular weight, because it can do a dipole-dipole with the water and the carbonyl and a hydrogen bond with the water. So it has two different interactions helping it pull it into water. So carboxylic acids tend to be the most soluble of the organic compounds in water. And it also has some acid-base properties that we'll talk about next. Okay, so even though we have this very long chain right here, and in the case of this compound here, we have what we call decanoic acid, which means it has 10 carbons in the chain, okay? So normally after about 5 carbons or so, you can't get an aliphatic compound. Actually about 2 or 3 carbons, you can't get an aliphatic compound into water. For an alcohol, you can get about 5 carbons into water. For just a main chain, for a carboxylic acid, we can get about 10 carbons into water. Notice our solubility is dropping off a bit here. And it has to do with the fact that it has this long hydrophobic tail, or tail that doesn't like water, but this head that has this polar hydrophilic, or does like water. Okay, and so by adding a little bit of base such that you make this into a salt, you end up getting things that are called surfactants or soaps. A lot of soaps they'll be like decanoic salts or laurate salts. Those are actually what we call fatty acids. They have these long aliphatic chains and a carboxylic acid. This part dissolves in water. This part will dissolve away fat. And that's how these long chain carboxylic acids, number 1, dissolve in water. Number 2, help dissolve oils and fats, because this half dissolves the oil and fat. This part right here, keeps it in water. So the hydrogen bonding and the dipole interaction of that group is very, very strong. All right, questions on goal number 1, naming and properties. Go ahead and chime in or put it in the chat. I'm going to move over to goal 2 since we have a decent amount of time. And we'll probably finish this off before our first half is done. Okay, so the next thing I want to talk to you about is the acid-base properties of the carboxylic acids. And as you would imagine, because we're calling it an acid, it's, it should have an acidic proton, okay? And we know that the hydrogen is the part of the carboxylic acid is the proton. And we call this a weak acid compared to things like HCl and HBr. However, it's a strong acid for an organic compound, okay? So our pKa for our carboxylic acids runs between 4 and 5. There's some things that affect that property, and we'll talk about that in a minute. But the idea is that once you add a carboxylic acid to water, it's going to go ahead and dissociate partially and partially dissolve into water, giving you the acetate ion and protonated um, water or hydronium ion, okay? So this is shifted a little bit to the side where no matter how much water we add to the system, it will never fully dissociate. That's because there's always a little bit going back, a little bit of this acetate acting as a base and pulling off a proton from the hydronium ion. So there's always a little bit going back. So we have our equilibrium constant here. It gives us our pKa of 4.76, and that's for acetic acid, okay? Now, you can, when you dissolve this in things like an alcohol, you can actually change the relative acidity by this because it has a different stabilization by having more hydroxyls, and the protonated alcohol is less acidic than the protonated water. Okay, so let's talk about how we can change the strength of the carboxylic acid. Now, one way we can do that is by adding electron withdrawing groups to the group near the carboxylic acid, okay? So if we look at just the acetic acid right here, this is one we just saw on the other page here, we only have carbon-hydrogen bonds and then a carbon-carbon bond between the CH3 and our carboxylic acid, okay? Remember that carbon-carbon bond is basically non-polar, okay? By adding an electron withdrawing group, like chlorine, chlorine is much more electronegative than hydrogen, and therefore it's starting to pull electron density away. It's starting to create a more polar carbon-carbon bond. And we see this because it makes it easier to remove the proton. It makes it easier to remove the acidic proton off of the acetic acid. And as such, our pKa goes down. Remember, as we go down towards 0, we're going to stronger and stronger acids, okay? Now, you can also add a second one, and that's going to pull even more electron density away from the carbonyl, making it even more acidic. We've now dropped it by almost 3 points. And so we can make it even go down further. By adding a third chlorine to the system here, we get it to almost a strong acid. We almost have it completely down to 0. Once we get down to 0, that becomes a strong acid fully dissociated in water. And that's all has to do with the fact that these electron withdrawing groups are increasing the stabilization of the anion because they're pulling electron density away from this negative charge, making it easier to lose that hydrogen. So this is how acidity is increasing in a carboxylic acid by adding electron withdrawing groups. And we call that the inductive effect because it's pulling the electron density through one or more bonds. So it's an inductive effect. Okay. So this inductive effect falls off the further you get away from the carboxylic acid because you have to pull it through more bonds. So let's start here, which is the least acidic system. So we've actually flipped the bar, so be careful of that one. If we think about this compound here, we have carbon-carbon bonds, which are nonpolar. So we should have no inductive removal of electron density from our carboxylic acid, okay? If we put one chlorine right next to it, right here, we drop the pKa from the 4.8 to about 2.8, so about 2 points by having it directly next to the carbonyl carbon, okay? If we move that chlorine over just one position, now it has to pull electron density through one extra bond. So now it has to pull electron density through 2 bonds. And notice our acidity doesn't change as much. It was 4.8 and now it's only about 4. Okay, so now because it's moving electrons through 2 bonds instead of just 1 bond, there's less of an effect. Okay, and now we can barely see any effect by moving it over 1. So now we have this chlorine is pulling electrons through 1, 2, 3 bonds, and we barely see any effect at all, about 0.3 on the pKa. Okay, so when it's pulling 1 bond, it's about 2. When it's pulling 2 bonds, it's about maybe 0.75. When it's 3 bonds, it's barely 0.3. Okay, so the further you get away, the more rapidly it decreases the effect on the acidity of that acidic carboxylic acid proton. Okay, so we can use this to our advantage, because what we'll know is that when we use the carboxylic acids, by adding just a little bit of base, we can get them to go into water. Okay, for example, in the case of benzoic acid, it's very poorly soluble in water. In fact, in some of the labs we do, we actually recrystallize benzoic acid from water. It dissolves when it's really, really hot, and then when it comes out of solution, it makes these big, nice needles. Well, to help it go into water, all we have to do is pull off this proton, and now we have an ionic species here, our benzoate, or our carboxylic acid salt. Okay, when we have our carboxylic acid salt, we not only have our hydrogen bonding aspect to it, but now we have our ion dipole and ion hydrogen bonding, which pulls even more of those carbons into water. So here we're pulling 6 carbons into water. And we'll see that same effect not only with just our standard bases like sodium hydroxide or potassium hydroxide, but just the Lewis base of ammonia will do it as well. A little bit of ammonia in water, this ammonia acts as our Lewis base and will deprotonate it, giving us our new Lewis acid and our counterbalancing carboxylic acid salt. When we have a carboxylic acid salt, we call it a benzoate, or I'm sorry, a carboxylate, or in this case, a benzoate. Okay, so we can use this acidity to our advantage because the acids of the carboxylic acids are more acidic than the protons of alcohols. So we can use that to help separate an alcohol from a carboxylic acid. Okay, so in the case of something like acetic acid right here, it is actually so acidic we can use an even very mild base like sodium bicarbonate. Okay, sodium bicarbonate is sodium carbonate, or is a carboxyl carbonate, carbonic acid that's had at least 1 proton removed by a base to giving it, so it still has 1 acidic proton, but when it has that last acidic proton removed, it can act as a base now, and it removes a proton from the carboxylic acid to give us our carbonic acid here. Okay, and then carbonic acid actually decomposes into CO2 and water. So that when we take acetic acid and our sodium bicarbonate, we end up with our sodium carbonate as a nice stable molecule, and CO2 and water go away. Notice these arrows are not reversible. The reason they're not reversible is that when the CO2 leaves the water, there's nothing there to act as our acid. The water is not acidic enough to protonate our new base here. So when the carboxylic acid goes away, we end up with a nice clean salt of the carboxylic acid. Okay, so we can use a very weak base like bicarbonate to deprotonate a carboxylic acid. Okay, bicarbonate is not a strong enough base to deprotonate an alcohol. So we're going to use the advantage of having a carboxylic acid be more acidic than an alcohol to help separate a mixture of the two. So the idea here would be we could dissolve these 2 compounds, because they're both barely soluble in water. We're going to solve them up in a solvent that's not water, and we're going to add a strong base to the system here. In this case, it's sodium hydroxide. Now, sodium hydroxide is not a strong enough base to deprotonate our alcohol here. And therefore, our alcohol stays in our ether layer, okay? Now, our sodium hydroxide is a strong enough base to deprotonate our carboxylic acid, meaning it's gonna get pulled into the water layer. It is now water soluble, okay? So all we have to do is re-acidify the system and it will precipitate out as our nice solid that's pure. This will have to evaporate off our ether to get our material here. So we're using the acidity of our carboxylic acid to act as a way of separating our materials. Okay? Questions on acidity. The three things about acidity is all carboxylic acids are weak acids, i.e. not fully dissociated in water. Even weak bases like carbonate can, and bicarbonate can deprotonate them. And we can use that salt to make them even more soluble in water than they were in their neutral state. Oh, and the inductive effect. By adding electron withdrawing groups nearby, you can increase the acidity of your system. All right, any questions on that? We are right at about 12:36. I'm going to start on goal number 3 for the next couple minutes, and then we'll break at 12:40, okay? Because right now we're going to look at the reactions of our system here, okay? So, and we've already learned one of the reactions that our carboxylic acids do, which is that it will react with base to form a salt, okay? So, but our next reaction is the fact that we can, just like we did with aldehydes and ketones, we took aldehydes and ketones and we could add hydrogen across that carbon-oxygen double bond. Okay, when we add that hydrogen across that double bond, we reduced those down to alcohols, either primary or secondary alcohols, okay? In this case here, we reduce our carboxylic acid using our reducing reagent. If we used sodium borohydrate, which is what we used to reduce down an aldehyde, it doesn't work with carboxylic acid. That OH on the carboxylic acid doesn't let it do it. However, the other reagent we learned about in the last chapter is the lithium aluminum hydride, okay? This was the stronger one, okay? So if we have an aldehyde or a ketone and we just want to reduce that, we can use this reagent here. But if we want to reduce our carboxylic acid group down, we have to use lithium aluminum hydride. So this is where chemistry starts to get fun, because you can choose an exact reagent to react with just one functional group and not the other, okay? So while this will reduce both aldehydes and ketones, both of these reagents will reduce aldehydes and ketones down to alcohols, only lithium aluminum hydride will reduce carboxylic acids down. And it always reduces them down to a primary alcohol. That's because it reduces off the entire oxygen here. So that gives you 2 hydrogens that it's adding to it. So carboxylic acids always yield a primary alcohol. Notice this double bond over here isn't touched. Just like before, the sodium borohydride and the lithium aluminum hydride do not touch alkenes. They only touch carbonyls, okay? Okay, so that takes us right up to about 12:40. I'm gonna go ahead and break here, and we're gonna come back and finish up chapter 13, goal 3. We might get into chapter 14, which is carboxylic acid derivatives as well. So I'm gonna go ahead and stop recording. You can, well, let me stop sharing first, and then I'm gonna stop recording.